Good evening, everyone, and welcome to the 12th webinar organized by Pallavan Learning Systems. Before we delve into today's webinar, I would like to say a few words about Pallavan Learning Systems, or PLS. We are an educational research organization that primarily focuses on the concept of learning how to learn and believes in promoting learning in all various facets and its diverse forms. One of the main objectives of PLS is to conduct research, organize seminars and conferences, and we do this for the creation and dissemination of new knowledge so that what we do at PLS remains current and relevant to the rapidly changing times. We've conducted many of such webinars in the past. Some of them are on the following themes: the future of learning, nurturing our learners in the times of COVID-19, developing a thriving community approach to promote learning, the irrelevance of formal education, do degrees matter, the unseen revolution, technology, education, and life, and a previous webinar, which was on assessment, valuing what matters. If you're interested in any one of these webinar topics and would like to learn more, please do reach out to us and you will be delighted to share the detailed reports on them. You can also find more such resources and the reports by logging into our portal through pallavanlearningsystems.com. You will find the link in the chat soon. Now coming to the present webinar, the third episode in the series are On a Quest to Learn, a series on evolving nature of one's learning journey. The theme of today's episode is teaching mathematics with the help of history. Mathematics is often seen as abstract, complex, and detached from the real world, and it's misunderstood that way. However, at Pallavan Learning Systems, we believe that mathematics is a language, the language of the universe that helps us to make sense of the physical world around us. During this webinar, we will strive to make mathematics accessible, understandable, and relatable with the help of history. By providing context, showing the evolution of mathematical ideas, offering engaging narratives, highlighting cultural perspectives, educators can actually make mathematics come alive in the classroom. This approach improves understanding and also inspires a lifelong appreciation of the beauty and significance of mathematics. Through history, mathematics can become a story of human achievement and innovation, connecting students to the global intellectual tapestry and encouraging them to embrace it. At the core of this webinar series is the philosophy of learning practiced at Pallavan, which espouses that as learners journey along their individual path, their experiences help them to develop capabilities or skills while discovering or strengthening processes that help them acquire these skills. And as they travel this path, they acquire skills and understand processes. Learning also cultivates qualities of character that we refer to as watermarks. Before we begin with the talk, I would like to inform the audience that if you have any question during the talk, you can post the questions in the chat box. They will be taken up later in the Q&A session. I'm truly honored to have with us Padmashri Dr. Dinesh Singh, who will be taking us through this journey. Dr. Dinesh Singh is a Padmashri Awardee and a former Vice Chancellor at University of Delhi. He was also a member of the Scientific Advisory Committee 2011 to 2018 for the Union Cabinet, Government of India. He has pioneered several new ideas in the realm of education and on the role of technology in education. He has delivered world over numerous prestigious public and keynote lectures on education, on policy towards education growth, on mathematics, on Gandhi. He has also authored and edited several books. To be honest, if we talk about Sir's involvement and achievements, it might take the whole hour of the webinar. So I will let you hear Sir, and it will be an honor for all of us to hear what he has to share with us. Thank you for taking out the time to speak with us, Sir. I invite you to take us on this journey. Thank you so much.
Thank you. Thank you very much, Poojan, for all your praise, of which I'm not sure how worthy I am, but I'm definitely highly appreciative of your words. Thank you so much. And I'm delighted to be once again present on your platform. I think this is a great idea, and I think many good things have already happened on your platform. and I hope I can do justice to your aspirations. I deliberately chose this topic of teaching mathematics through the lens of history. There are many reasons why I have done that. One of the things that I have found, largely in those parts of the world where I and you live, but in other parts also to a large extent, that we have in our own times isolated subjects, put them into silos, and we somehow do not allow them to connect, to have synergy with each other. And to my mind, this is harmful, as I have learned from the lessons of history. You know, we mathematicians believe that God is a mathematician, and maybe one day I'll speak on that. But what do I mean by that very briefly? So no matter where I see in nature, wherever we exist, in howsoever ways we interact with the world, I find mathematics behind it. The problem arises when we isolate mathematics from the context in which it has been discovered, the way it has been applied, and that's when a large number of students and learners tend to have some difficulty with mathematics. So my purpose in this talk, of course, in one single talk, I'm not going to be able to solve any major issues of pedagogy or such learning. However, my idea is to sort of project a way forward. And the theme of my talk would be that one must try and be as transdisciplinary as we can in on our learning teaching enterprises. That would be my main theme. Excuse me. So without further ado, let me just get on with the theme of the talk. And let me also tell my listeners in advance, my viewers, listeners, howsoever they are connected today, that I am largely conversant with those aspects of history in the context of today's talk that relate to my own geographical area. So you will have to be a little patient with me. Many of my illustrations will come from this region. However, they are relevant in the context of a global viewpoint. So it's not that they're going to narrow your viewpoint, perhaps even enlarge your viewpoint. So, you know, I would like to go to the time of the Indus Valley civilization. And it's an amazing civilization. It dates back to more than 2,000 years before the time of Christ. So altogether from today, certainly more than 4,000 years old. However, there are issues of dating that seem to tell me that there may be other things here that we are missing. Today's talk is not connected with dating of these enterprises, but howsoever we try and date the Indus Valley civilization, it is certainly at least 4,500 years from our time backwards. So that's a really ancient civilization and very sophisticated, extremely sophisticated. Where did this civilization happen? So if I could have a look at a visual of the Indus Valley civilization, can I see a slide here that will show me the Indus Valley civilization? There you are. Look, can you see how sophisticated it is? It's about 3000 BC, as I've put down here. In fact, my contention is even older than that. But you can see that these are urban cities. These are all structured in a very methodical architectural way, very sophisticated. They use baked clay bricks. And they are using, you cannot build such civilizations unless you have sophisticated mathematics. And if you look at the geographical region, as the next visual will show you, you get an idea. The yellow marked region, that is more than 1 million square kilometers, that's where this civilization largely flourished. And even as I speak with you, there are new discoveries that are being made in the context of this civilization. More and more new things come about, new sites are being discovered, and you will see that they did marvelous things, and such things can be possible only if you have mathematics that allows these things to happen. The problem, the tragedy with the Indus civilization is that we have not been able to decipher the script. There are lots of seals that have survived, and you can see characters on the seals. But for some strange reason, we have not yet deciphered the script. So we have to make intelligent guesses. One of the most intelligent guesses that I have come across tells us that they wrote from the right to the left. So, I mean, when we write in the English language, the script, the Roman numerals, then we write from the left to the right. Without knowing what the script is, without deciphering it, we can tell that it goes from the right to the left. And the only reason why we can deduce that is when you look at the seals that have survived, which have clay seals and other seals where they have inscribed loops, then when you look at the way the loop is moving, you can tell that they're moving from the right to the left. So you can make those intelligent guesses without understanding the script, but the script remains a mystery. However, they had fairly sophisticated mathematics, else you could not make these kinds of designs and these kinds of buildings. And what I want to tell you is that even though it ranges over 1 million square kilometers, they had achieved a great deal of standardization. So I'll try and show you in the next visual image of a brick from the Indus civilization. All the bricks that they had manufactured in this vast territory, look at the standardization. They were always in the proportion of 4:2:1. That's the amazing part of this story. So you can understand that they knew the value and importance of standardization. They understood proportions. There are other things, as you will see. They also they understood fractions very well. How do we know that? So as the next visual will show you, they had a system of weights. And you can see those weights over here. They used a standardized system of weights, which were always based on the ratios 1/16, 1/8, 1/4, half, 1, 2, 4, 10, 20, so on and so forth, with the unit weight approximately being 13.63 grams. Now, that's a pretty good standardization. And the heaviest known weight was about a little more, almost 11 kilograms. And the lightest was in some centigrams. So these weights were in regular geometrical shape. Here you can see that they're all in the shape of cubes. They also had other kinds of things, barrels, cones, cylinders. Now you can see the shape of the cube is so well crafted. All this indicates that they had very developed ideas in science and technology, and until we unravel the script, we're not really going to be able to see too much, but you will also see the other things later as time goes by that come after this civilization. The last thing that I want to show you here is that they also had a pretty good idea of lengths and measurements. So, you know, the units of length were the Indus foot and the Indus yard. And both of these are a little more than the regular foot that we use and the regular yard that we use in our times. But they had pretty sophisticated ideas of standardized foot and yard. And they used, no wonder they could construct such sophisticated buildings. If you looked at the buildings in Mohenjo-daro and the plumbing system that they had devised, that will give you a much better idea of how this was going on. And we could move on to some other things in the next visual. So, you know, all of us deal in our school with a certain theorem in geometry. I have found no evidence of that theorem in the Indus civilization, but it's a theorem that is known across the world, no matter where I have traveled, no matter howsoever scared people are of mathematics, they all know the name of this theorem. That is the theorem of Pythagoras. Now, there is an amazing story behind the theorem of Pythagoras. You know, Pythagoras lived sometime around 500 BC. And in India, there are textual records to show that in India, we knew this theorem hundreds of years before the time of Pythagoras. There is an ancient Indian text called the Satpat Brahmana. That is certainly 400 years before the time of Pythagoras. The Satpat Brahman tells you exactly what the theorem is. It enunciates the theorem. It gives you a clear statement. Sometimes Western scholars say that, oh, yeah, okay, they had a numerical idea of the theorem, but they didn't know how to prove it. And Pythagoras actually gave us a proof. In Euclid's geometry, you will find a proof of the theorem of Pythagoras. My point is, if you discuss this with your students when you teach mathematics and you talk about how these things have come about, it isn't that one day some author of the Satpat Brahman got up and wrote that here is the statement of the theorem. It comes through natural needs of society. And that's what I will try and show you in the next visual. So if you look at the next visual, you see that diagram over there is actually what is called a fire sacrifice altar related to Vedic practices. So this is the time when the Rig Ved and other Veds were being developed and practiced in a large part of India. And most Vedic practices and sacrifices required a fire ritual. And for the fire ritual, you had to construct altars. Different rituals, different needs for fire sacrifices required the altars to be constructed in different ways. They had to have different shapes, different areas, different requirements. But they were very sophisticated requirements. You can just see one in the image here, and you can see that this is a square inside a square, but not fitted in a concentric fashion. There's a slight tilt to the square, and there lies the proof of the theorem of Pythagoras. But what happened really? What was this all about? So, when the Rig Ved and the other Veds, and these are matters of history, so I'm not speaking from chauvinistic viewpoints. When the Rig Ved was being practiced in India and these fire sacrifices had to be performed, we had very specific requirements of how you construct them. And for that, you needed mathematicians because they had to make measurements, they had to make constructions. So there is clear evidence that mathematics and architecture and design in India, hundreds of years before the time of Jesus Christ, were working in harmony with each other. And so for all the constructions and designs of the fire sacrifices, a whole body of mathematics grew in India. That mathematics is embodied in a series of texts. 16 of them certainly existed. There may have been more, but we have evidence for 16, and a little more than 10, maybe 11, all survived till today. How do I know there were 16? Because these 11 or 12 refer to the other texts which we can't find in these times. So there were certainly 16 of them. Now, what are these texts? They're called the Shulba Sutras. And each of these Shulba Sutras, there are 16 Shulba Sutras, each of the Shulba Sutras has a mathematician's name associated with it. What does Shulba Sutra mean? And you will be surprised pleasantly, I believe, to learn what it means. Shulba actually means a piece of cord or string, as it says here in the slide. Sutra means certainly a formula or an aphorism. So all these texts embody mathematical formulae that arise from the use of a piece of cord or string. Now, what does that have to do with sacrificial altars and constructions and architecture? Well, even today, if you go to any construction site in India where buildings are being constructed, you will find that the mason has a piece of string with a dead weight attached to it. And he uses that to good effect for all kinds of bricklaying and designing and aligning and so on. The Shulba Sutra is precisely that dead weight and the formula that come to be associated with the dead weight. So a whole body of mathematics in India grew out of the needs of constructing these things through architecture, through design, and these were societal needs. So when we come to the theorem of Pythagoras, which the next visual will give you a better idea, one of the best things that you find is these are diagrams that are described in the Shulba Sutras. One of the Shulba Sutras has this actually as a statement over there. And the next visual will tell you of a very specific Shulba Sutra. So this is the Shulba Sutra of Bodhayan, as you will see in the next visual. What Bodhayan existed in 800 BC, and the Shulva Sutra of Bodhayan actually not only, so this is my counter to the criticism of Western scholars. Bodhayan's Shulva Sutra not only states the theorem, but he gives you a way of proving the theorem. It's a visual proof, but from that proof, you can actually construct a nice modern day proof without any new ideas added to it. Bodhayan, as I told you, was 300 years before the time of Pythagoras. Now, here's something very interesting about Pythagoras. So, when I delved into why we ascribe this theorem to Pythagoras, and I had to refer to many Western sources also, I actually found that Pythagoras had a disciple from the school, the Pythagorean school, called Opelius. Opelius actually has given a series of lectures. They are known as the Florida lectures. They're all recorded. They were all in Greek. He was in Alexandria. And Opelius says categorically that his master went to India to learn from the Brahmins on the banks of the Ganga. Others have also said this. I tried to find out. Opelius also says he was deeply influenced by Jain philosophy. He calls them gymnosophists. These are Jain munis or Jain ascetics. And Pythagoras was so heavily influenced that he turned a vegetarian and he stopped wearing leather garments. These are all principles of Jainism. Also, he began to eat his dinner before sundown. These are all principles of Jainism that a good adherent has to practice. And Pythagoras was deeply influenced. There are others who say this. Voltaire, as you will see in the next slide, Voltaire, the French philosopher, who was around the time of Newton, also records that I'm convinced that everything that has come down to us from the banks of the Ganga, astronomy, astrology, spirituality, it is very important to note that Pythagoras went from Samos to the Ganga to learn geometry. Now, this is Voltaire writing several hundred years ago. So this gives you a good idea that Pythagoras was actually connected to Indian geometry. And I went to a place of Indology. Great scholars live there, Ujjain, very close to Indore in a western part of India. And I met those scholars, and they also told me that they have enough traditional records to tell them that he came to India. Now, does it mean that he stole the theorem? Not at all. He came here, he interacted with all our scholars, and he imbibed some of these ideas, and he went back, and he must have enunciated them later on, because these pieces of knowledge moved further to the West through the Greek school. Because the Greeks had put them down in systematic fashion, their names were attached to these discoveries. But the fact is that many of these things have come to us from Indian sources. And I will try and show you something in the next slide, which will be of great deal of interest. So there is another visual that this is from the Shulva Sutra of Katyayan. Katyayan lived 200 years before the time of Christ. So he was certainly after Pythagoras. But Katyayan was an amazing mathematician. By the way, what you see in the shape of a bird is a fire sacrifice altar. Again, you can see that they are all in precise geometrical shapes. There are triangles, there are angles, there are squares, so on and so forth. And this is a huge fire sacrifice altar meant for a very specific fire sacrifice. But the most interesting part of Katyayan's Shulva Sutra, as far as I'm concerned, is that he gives us one of the best known proofs of the theorem of Pythagoras, which I think I'll be able to show you in the next visual. So you have this diagram in Katyayan's Shulva Sutra. If you look at this diagram, this is a square inside a square. And the way this proof is enunciated, not only does it give you one of the most elegant, beautiful proofs of the theorem, but it embodies a deep mathematical principle. And this works on the concept of areas. So this proof looks at the fact that the area of a square is simply square of the length of one side. So if a square has a side of length 2, then its area is 2 square, which is 4. And the area of a rectangle is length into breadth. That's all that this needs. And it gives you a beautiful, elegant, simple proof. And this comes from constructions in Vedic sacrificial altars. So that's where this comes from. And I will try and show you this in my next visual. So, by the way, I also need to tell you that they weren't only about these things. There were other things over here, but I'm not so interested in them right now. These Shulva Sutras understood irrational numbers and such things, and they had a very nice way of calculating values, like, for instance, root 2. If you use the method of the Shulva Sutra, you can calculate root 2 up to, I think, 6 or 7 decimal places with great accuracy, at least 5 over here, but I think there's more than 5. So there were other things here, but I'm really interested in the theorem of Pythagoras. So we'll look at the next visual. And let me just tell you that before I show you the proof, one of the things that bothers me is that when we teach this theorem, we don't ever give any practical relation of this theorem to the real world. If you look at the Shulva Sutra, it tells you that the theorem comes in a natural way from constructing the altars, because the altars needed area. And I'll come to that in a while. But here in this diagram, I want you to look at this carefully. I'm going to use, and this idea actually comes to me from ancient times, not Indian. I believe it's probably Egyptian or something related to Alexandria. Leave that aside for the moment. This is an idea dating back to hundreds and hundreds of years. And it is a very beautiful application of the theorem of Pythagoras. It allows us to calculate the radius of the earth. And the moment you know the radius, then you know the circumference. So you know the size, the dimension of the earth. How does it work? Now, before I come to that, and you can work it out, because I'm sure this will be on record and there is a small calculation here. But my point is this. I urge teachers, when they teach this theorem, to look at some of these nice applications. And then they will see that, this isn't just a theorem for us to, entertain our minds, intellectually make us happy, or scare some people. They have great practical needs. Up until at least a few decades ago, maybe 30, 40 years ago, in many parts of northern India, I know that when they would demarcate agricultural fields, and when they didn't have these precise instruments of measurement, they would use the theorem of Pythagoras to make sure that the lines at the corner of a field meet at a right angle. So all they would do is, when two lines met at the corner and they wanted them to be at right angles, they would make sure they mark a length 3 on one side and a length of 4 on one side. And if the diagonal was of length 5, then because of the theorem of Pythagoras, it's converse really, then that angle there at the corner would have to be 90 degrees. And that was one of the practical uses of the theorem. But here you will find a profound application. And I don't know of any school that I have visited, not just in India, but other parts, where they actually teach you that here is a nice application of the theorem of Pythagoras. So, look, suppose that semicircular thing is half the earth. I just need to know the radius, which I have designated as x. So from the center of the earth, there are two rays emanating to the arc, which is the boundary of the earth, both of length x. And the length y from the surface, which is a vertical line that goes up, is some object of reasonable height. Not very high, but maybe a reasonable mountain, or in today's times, you could just take a hot air balloon and go up maybe, a kilometer, or maybe even less, half a kilometer. And from there, you look at an object which is actually at the horizon. So that's where the right angle is being formed. So if I have an object at the horizon and I connect the tip of the length y to to that object, then because it is on the horizon, that line and the line coming from the center of the earth and touching that object, the horizon would form a right angle. You can work this out. And now, remember this length y beyond the surface of the earth compared to the radius of the earth is very small. And therefore, when we make a calculation, we make an approximation. I'm not going to give you a precise radius of the earth. Incidentally, you cannot have a precise radius for various reasons. One, the earth is not a perfect sphere, but our idea is to get some good approximation. That's the way the real world works. And I want teachers to understand this also. You know, we always talk of these precise numbers. That's all very good. But also teach your students this idea of how to approximate, because in the real world, everything works as an approximation. All measurements are also approximations. So if I tell you to measure 2 inches by scale on a piece of paper, and you draw a line which you say now 2 inches because you measured it against a scale, and you mark that dot or a line to mark 2 inches, remove the scale, and if you think that's 2 inches, wait till you enlarge it, magnify it 1,000 times. Then you tell me, where does the point give you 2 inches? And if you think now you can do that, magnify it 5,000 times, and you'll find that you're not sure where 2 inches will actually end. So my point is, every measurement is an approximation. Coming back to this idea, what am I doing here? So look, I'm going to apply the theorem of Pythagoras. I know from the top of the tip of the object, which is of height y from the surface of the earth to the horizon, that length is z. Now that can be known for various reasons. It's very easy to find out. So you have that length. What you don't have is x. And you know that y is very small, and you know y's length. So you know y and you know z. By the theorem of Pythagoras, x plus y is the hypotenuse. Its square will be the sums of the squares of the other 2 sides of the triangle. So you will get, as you can see below the diagram of the earth, x plus y square is x square plus z square. Now, if you expand x plus y square, and I haven't written that, but you can try this, it's trivial. Any 6th, 7th grader or 8th grader can do it. Then that ends up with x square plus y square plus twice xy. Now, if y is small compared to x, then y square will be even smaller. Let me illustrate this in the following way. If I have the number half, it's small, it's half. If I square it, it becomes 1/4, even smaller. So y square is something like that in comparison to x square. So I ignore y square, and then I have x square plus twice xy equal to x square plus z square. And from there, I simplify for x. I eliminate x square from both sides, and I simplify for x, and I get the radius of the earth, which is x, as z square divided by 2y. And they actually did it in ancient times, hundreds of years ago. And they got a pretty good value. That is the interesting part. And there are other things that you will see connected with the theorem of Pythagoras. If I can show the next visual, then I might be able to give you some more ideas. So, you know, oh, by the way, yeah. So talking about the earth, let me also tell you, I forgot about this visual. That, you know, you can use simple ideas of parallel lines also to measure the circumference of the earth. Again, this was done before the time of Christ by a Greek mathematician who was actually a polymath. He was also a librarian at Alexandria. His name was Eratosthenes. And he came up with a marvelous way of computing the circumference of the earth. And his answer, his measurement was also a very good approximation. So what did Eratosthenes really do? The first thing that Eratosthenes observed, and I want teachers, if there are any teachers who are here on this webinar right now listening to me, I want you to understand that unless you do things in a practical way with these mathematical ideas, it's going to be very difficult for your students to really enjoy them, to grasp them. And so think about this. Talk to them about who was Eratosthenes. And Eratosthenes did other things in mathematics. Prime numbers are very important for mathematics. You know, all of cryptocurrency and all the manipulations and all the speculations and all the dealings of cryptocurrency rely heavily on finding prime numbers. That's where all the mining goes on. And it isn't just there. You know, when you and I talk, and most probably, I'm not sure, this technology that is being used will be using a kind of encryption that cannot be corrupted during transmission by hackers. That technology also relies on a method that uses prime numbers. And whenever we send an email, if I write something like meet me tomorrow at this place as an English text via email or even via WhatsApp or Instagram, then that text gets converted into a mathematical message, simple numbers. And then they encrypt it, they have it coded so that no one can hack it, no other person can read it. If you look at WhatsApp, they tell you these methods have end-to-end encryption. All these encryption ideas essentially rely on the fact that they are using prime numbers. So, and the people who first invented one of the first methods of encryption along these lines were three mathematicians from Israel, Rivest, Shamir, and Alderman. And they have become multimillionaires because they have the patent on this technology, which every such device uses. And there are other methods which also yield a lot of revenue for people who have patented them. All of them are dependent on these simple mathematical ideas. My worry is, and these things I have taught to school children. I have taken school children from the 10th, 11th grade who have been good at coding, teach them a little bit about prime numbers, and then they can write codes that give you these encryption methods. I've gotten them to do that. The sooner we bring these practical things connected with mathematics into the curriculum, the better it will be for all of us. We cannot and should not teach mathematics in abstraction on the board. When it comes to measuring the circumference of the earth, I first showed you the method that uses the theorem of Pythagoras. Here's another method. This goes back to, as I told you, Eratosthenes, who was before the time of Christ. And what was Eratosthenes' idea? The first thing he understood was that the rays of the sun, the light rays of the sun, when they start from the sun, they are not parallel to each other. But because the earth is at a long distance from the sun, by the time these rays hit the earth, they are parallel. How do I know that? Well, there are many experiments by which you could do that. I'm sure if you look at some of these ideas on YouTube, you'll be able to find some of these experiments. But here's one simple experiment that I've had many colleagues perform in their classrooms, and students immediately grasp that idea of why, even though the rays of the sun, when they start, are not parallel to each other, but the ones that hit the earth, by the time they hit the earth, have become parallel. All you need to do is to take a long piece of string, very long, say maybe 40 meters or 20 meters, and then take a needle or a pencil and wrap the string around that pencil and take the other ends to the extreme end of the classroom. So make a student stand in one corner with the pencil and the string goes around the pencil, and keep it taut at the other end, so 10 meters from the pencil, or a little more, and hold the two ends straight and as close to each other as possible. Now remember, these two ends of the string are actually coming from a single point, the pencil. So at that point near the pencil, they are not parallel. By the time they come to the other boy standing at the other end of the classroom, holding the strings taut and pretty close to each other, the last 6 inches, no instrument can tell you that they are not parallel. That is why the rays of the sun when they hit the earth, become parallel, even though when they start, they are not parallel. My thing is, get students to perform these experiments. You also teach them about parallel lines in class and you talk about alternate angles, but I have no idea if you ever talk to them why these angles, why this kind of geometry is important. I'm just giving you one idea that dates back to ancient times, yet I haven't seen schools talk about this. So what did Eratosthenes do? You know, let's look at these three rays coming from the sun in the diagram here. R1, R2, R3. These are three rays hitting the earth from the sun. This is just a visual representation of the sun, just to make things a little clear. So just take it that way. But as they are reaching the earth, they become parallel. Now, the ray R3, as Eratosthenes observed, at the summer solstice, and now I ask you to go find out what is the summer solstice. But at the summer solstice at 12 noon, the ray actually hits the earth at a perfect right angle. So if you look at the surface, and if you have a well that goes down straight vertically from that point where the ray R3 hits, then at noon, summer solstice, in Aswan, in those days it was called Cyan. Aswan is in Egypt. At Cyan, as the red dot shows you, that ray will go straight to the bottom of the well and completely, it will cast no shadow on the well. So the bottom will be completely lit. There'll be no shadow. And therefore that ray goes and touches, you can imagine hypothetically, the center of the earth. That's why the center of the earth I've designated as C in the diagram, and the ray R3 at the summer solstice at Aswan, which is today Aswan, but in Eratosthenes' time, it was known as Cyan, the ray goes straight to the center. Then what Eratosthenes did was, at exactly that time, he had a man move a distance D from that well in Aswan. So that distance D he knew. And now there is a ray R2 that goes and touches the point at the length D from the well in Aswan, that where my arrow is pointing. You can see that? Yeah, the cursor. You can see the cursor there. And at that point, he had the man embed a vertical stick. So he put a vertical stick, which is of some length, not very long, but a vertical stick. And then he looks at the shadow cast by the vertical stick by the ray R1 coming from the sun. Okay, so all he did was, when you look at the shadow cast, then where the shadow goes to the tip, from there you touch the tip of the stick, and you look at where the stick is embedded, there is an angle that is alpha. Let's call it alpha. Then because that R1 is parallel to R2, then the other angle that I have marked, that is an alternate angle. You can treat this ray coming from C, which is really the stick, when it goes above the surface of the earth, it becomes the stick. Okay, so that's a transversal for the rays R1 and R2. And a stick is really the transversal, and that stick is casting a shadow. The angle that the shadow makes with the tip of the stick is alpha, and that will be the angle equal to the alternate angle made between R1 and R2 by the transversal, which is the stick. So that's alpha. You get it? Now, that's vertically opposite to the angle alpha, as you can see in the diagram over here. So R2, if you were to extend it into the earth, then R2 is parallel to R3 because these are rays of the sun, and R2 is parallel to R3. The stick, if you were to extend it because it is vertical on the surface of the earth, it will go touch the center of the earth. So again, it remains a transversal between R2 and R3. And so the angle between the ray R2, if it were extended into the earth, and the stick, if it were extended to the center of the earth, would be alpha. And the R1 and R2 treating the stick as a transversal by extending it to the center of the earth, makes you realize that the angle subtended by the two arcs, the arc that is formed between the stick reaching the center and the well at Aswan, that length which is marked off as length D, that subtends an angle alpha. Now, if an angle alpha gives you an arc of length D, then you can calculate that because the whole earth will form a 360-degree angle, what will be the circumference of the earth is simply 360 by alpha into D. You know D, you know alpha, you calculate the circumference of the earth. Look, I am sure because I've done a lot of hand waving and I know that this is not the best way to do it, you may or may not have fully understood. But my point is, I have performed this experiment with 6th grade girls, about 12 of them in Delhi, 12 of them in Bangalore. And I got them to embed a stick in Bangalore and measure the shadow at 12 noon. And I knew the distance between Delhi and Bangalore, the straight distance. And the girls, not only did they find a very good approximation to the circumference of the earth, but I took anonymous feedback from these 20-odd girls. All of them said that they really enjoyed the whole experiment. 2, they will never forget it. And 3, they understood the importance of parallel lines. That is the point I'm trying to make here. And I've used these ideas from history. You talk to them about Eratosthenes, tell them to find out there were other things that Eratosthenes did. He created a method to find prime numbers. It's such a simple method. It's called the sieve of Eratosthenes. And as I told you, prime numbers, if for no other reason, they're extremely important in the commercial world of fintech, in encryption. All governments, all private corporations use methods of encryption that depend on finding good prime numbers, big prime numbers, unknown prime numbers. And so if our students become adept at understanding the sieve method of Eratosthenes, then later on in life, because those sieve methods have been made more advanced, more sophisticated, of a higher kind, maybe they could get into these areas, become good coders, and apply these things and go into a different kind of world. Not every student is going to be a Ramanujan. Not every student is going to be a Newton. So we as teachers must understand that a large body of students are going into different areas according to what their heart tells them. Giving them these simple things to equip themselves for these ideas makes them better at whatever they do in life. Otherwise, if we keep teaching in abstraction on the blackboard all the time, writing things and giving them theorem proof, then that's not going to work. So that was the point I was trying to make. I am running out of time. I don't want to talk too much, but there's one other thing I want to teach you from history, the Katyayan proof of the theorem of Pythagoras. So if you could move to the next visual, here is a really easy proof of Pythagoras' theorem. And again, I don't want to scare you. This is a trivial proof. If you look at on the extreme left of the slide, I have stated the theorem. Right next to the rectangle is the actual triangle. The base has length A, the vertical has length B, and the hypotenuse has length C. And in the rectangular box, I have stated the theorem, A square plus B square is equal to C square. How do I prove that? So here's how Katyayan gives you the proof. And if you look at the image, it's a square inside a square. It already looks like a Vedic fire sacrifice altar. Even today, you go to any wedding or any other Vedic ritual for those who follow the Hindu religion, for instance, then you will find that sacrificial altars look a great deal like this triangle, square inside square that I have drawn here on the screen. So what did Katyayan do? If you had the triangle with sides that make the right angle as length A, length B, and the hypotenuse as length C, then he took a square of length A plus B. Okay? And you mark the lengths A and B on each side of the square whose length is A plus B. And if you join those points where A and B lengths meet, then you form the square C of length C inside the square of length A plus B. And now, what is the area of the large square? Its length is A plus B, so the area is A plus B square. But that is also equal to the area of the smaller square of length C plus the 4 identical triangles of lengths A, B, and C. Obvious, it's so obvious visually. What is the area of the smaller square? It's C square. Combine those 4 identical triangles into 2 identical rectangles of sides A and B. So now the area of the square, large square, is C square plus the areas of the 2 identical rectangles, each of side A and B. So it's twice AB. So now let me repeat this. What am I trying to tell you? The large square has area A plus B square. It is also C square plus twice AB. And large A plus B square is A square plus B square plus 2AB. And you have also equal, because these are equal areas, it's also equal to C square plus 2AB. Cancel 2AB on both sides and you will find A square plus B square is C square. That's Katyayan's proof. It's just a trivial visual proof. The idea is to represent the same area in 2 different ways. And that embodies a deep mathematical idea used in advanced mathematics. And it comes from a very practical application through constructing sacrificial altars for fire sacrifices connected to Vedic rituals. So my point is, and I had many other things in mind, but I have really exceeded the time I had set myself. And if the Pallavan Learning System is kind enough to invite me some other time, then I will show you some other ideas from the history of mathematics. I will also tell you about the story of the calculus and how the calculus was discovered and what is the amazing history, both Western and Eastern, and how the two have overlapped and there are still some mysteries. And I will also talk to you about simple probability theory and how it is connected to such practical real world needs. And that's how probability theory started. And if you teach these things in the context that from where they came, our students will understand them that much better and will also do better in life because they will see mathematics in action in the real world. But at this point in time, I would like to end my talk. Thank you for this patient listening. I at least enjoyed talking about these things. Hopefully, we shall meet again. Thank you very much.
Thank you. Thank you so much, Dr. Dinesh. I was just looking at the chat for some questions that would have come up during the talk. So I'm also inviting if there are some questions that we want to ask. I have a question right in front of me. Shall I go forward with it?
Please.
Haji. So initially, there's appreciation for the presentation. It's Choki says it was very fascinating. And the question is, what do you think is the best way for students to inculcate a love for learning mathematics?
So, there is no single universal formula, but by and large, with all students, in my experience, and I'm also in touch with some very gifted mathematicians who also are worried that school children tend to shy away from mathematics. So they have also performed experiments and they are in agreement with me. They are largely in the USA, but they are in agreement with me. They tell me that, most students would like to see mathematics in action, connected to things in the real world. That's what I've been trying to do even here in my talk. So there are a small number. In a class of 100, 5 will want to learn it in abstraction like Ramanujan. But 95 on an average would like to see it through a real world application. So when you talk about parallel lines, I said if you use how to find the circumference of the earth through parallel lines, then the students immediately begin to like it. And those 5% who really want to do it in abstraction will also like it. So for them, it will be an added bonus. So my humble suggestion is, one, don't teach too much. Believe me, not just in mathematics, at the school level, we teach too much of everything. At least I don't remember many of the things that were taught to me in school. I only remember those things that I liked, and there weren't too many. And the reason was because I was not given the freedom to do the things I wanted to do my way. Because there's always this pressure, and I don't blame the teachers too much. They're always told that, we have to finish this syllabus and do this and do that. And parents are always pressurizing teachers that why haven't you done this topic and that topic? So it's a complicated world. But I believe that there is a way out. After all, I did learn a whole bunch of things that were taught to me in school. I seem to have survived. Okay.
Thank you so much, sir. I think that really answers the question. There's another question that I think uh, first thing when I've been going through the comments, there's a lot of uh, a discussion on wanting to hear you more and get more of your insight on specific things like probability, calculus. There is a question specifically for prime numbers. Karma is asking, as you said, prime numbers are very important in our daily life. Could you share how maths teachers need to take this concept into the life of students?
Yeah, so first we must get the students to play around a little bit. They must learn to play with prime numbers and numbers in general. Forget prime number. How did Ramanujan become Ramanujan? No teacher really taught him. It was because he played around a great deal with numbers. And so, as Littlewood writes, that every number was his personal friend. And so, my humble suggestion is from an early age, allow students to play around with numbers in their own ways. What we do is we force them to memorize multiplication tables. Memory is good. I endorse that. But don't do it too much. Some students will memorize up to 20. I never memorized multiplication tables beyond 13. Never. And I have had no trouble in my life in making any kind of computation. I've been always had easy, you just have to do a quick mental computation, and I didn't go beyond 13. 15 is easy to remember, so technically you can say I knew up to 15, but I mean, that's it. I made no effort to remember any tables. And as I said, I have survived. So one, then allow them to experiment. What is an odd number? What is an even number? How are they spaced? Then why? For instance, I've asked teachers this. They have a rule for division by 3, 4, 5, etc., etc. But when I ask them, why do we have this rule for division by 3? Most school teachers are unable to explain this. Let the students experiment. The teacher should become a mentor and let them experiment in groups. So don't make one student compete against the other. Form groups of 5, 6, 7. Give them that task. Teach them a little bit about how to write this decimal representation of numbers. And then you watch how these students will begin to discover things. And now you have computers and you have artificial intelligence. You can perform amazing things. The world is changing rapidly. If we don't change ourselves, then we will, as teachers, we will get left behind the world and we will be at a loss. Do you know that the Khan Academy, Salman Khan, who runs the Khan Academy, he is now using GPT-4 and he is using his videos to give students personalized teaching of mathematics. Just think, so each student who enrolls there has a personal tutor. Just think how much we as teachers are in danger. So I urge teachers to start looking at the world through that lens.
Yeah, thank you so much, sir. I think a few of the questions that were coming up are already answered. Just trying to steer that towards those questions. There were a few questions, and I'm combining a few of them where some of the listeners are asking about. This is a wonderful approach, and but how do we make space for these experiments, activities in the curriculum and to keep the positive of time in place? What and in the times when you're talking about how Amigo bot and all of those things are already available, there is all the content is available. There is a AI bot that is talking to you and also explaining solutions and steps. What role does the teacher play in that case?
So, one of the things I was talking to some teachers connected with school mathematics, and they told me, and I was happy to hear this, in India, at least the NCERT has reduced the course content for mathematics a great deal. I'm told that they have reduced it significantly, and so there will definitely be room for these things. Second, somewhere we have to, you see, one of the pressures that comes to us is through parents. Parents are worried that if my child is not taught all these things, then my child will not be well prepared for competitive exams. And so schools come under enormous pressure because of this parental need to make the child competent enough to take these exams. Here, I think we as a body of teachers must talk to parents, talk to policymakers without being angry or without creating a ruckus. And because the NCERT, under the National Education Policy of India at least, and from what little I understand, in places like Bhutan also some very good beginnings have been made. So these are allowing us to give a certain freedom to our teachers. Let's grab it with both hands. And you can always cover all the basic things and do this. Believe me, I mean, I'm no fan of competitive exams. But if you master these basic ideas, then many students, and I know some students who have cleared competitive exams without going to any tuition center, without taking any special tutoring. Just have faith in your child. And also, these competitive exams are not the be all or end all of your child's career. I mean, in 5 years, I conducted an experiment where I took 65 odd students who liked maths, had not done well in any exam, and they have built brilliant careers connected to maths, engineering, technology, and discovery. And they are doing extremely well by any definition of what is extremely well, by wealth, by position, by power, by happiness. So there is a world outside there. I think the sooner we understand this, the better it is.
Thank you. Thank you so much, sir. I think my love for mathematics is also making me carried away and asking you as many as questions as I can ask. But I'm being told by my team that we are crossing the time. And thank you so much. I'm so grateful that we got the chance to hear you. We got the chance to interact with you. And it was really enlightening, inspiring. And personally for me, being related with mathematics education, it is so interesting that we often talk about uh, maybe time travel is not mathematically possible, but with today's session, it seemed as if we were traveling through time with the help of mathematics and seeing how mathematics evolved. And looking at the journey of a concept became so interesting, looking at how prime numbers started off and what are they talking about, how modulo arithmetic and how encryption and everything with cryptocurrency is using that concept, and you looking at the journey of Pythagoras theorem and looking at how, let's say, global positioning systems and everything is using all of that. And the journey of that concept is also something that really stood out to me. And I'm sure for all of the members of the audience, it was something that really stood out. And I'm so glad that we got the opportunity to hear you and talk to you about this. I would really like to thank all of the team members at PLS who helped in organizing the webinar, ensuring that the entire process was seamless. And you can find the links in the chat box to connect with us and to know more about us and to find more of our content on our portal and elsewhere. Finally, thank you to the member of the audience for listening in, for interacting in the chat, for posing questions, for engaging. Your participation helped in making this webinar actually what it is and adding value to it. Thank you so much. And we have learned a lot today, and we hope to see you again. And I'm sure that there is so much more that we would want to hear from you and talk so much about. Thank you so much, sir. And thank you so much, everyone.
Thank you very much. Thank you very much.